hand over to Tim Lanfear of Nvidia, and Tim's going to take up the theme of low power now. Thank you.
So Mike did come out into the hallway earlier on to check I was here, so he has been nervous about the speakers turning up this morning, so at least that's one problem off his mind now. Here is a picture of quite a variety of computing devices. So it starts on the left-hand side with a mobile phone, and we have a tablet and a game station and a laptop and a workstation and a server. And despite the immense variety and breadth of those systems, they all actually have one single thing in common. And what they have in common is that they are power-constrained computers. So the computer architect who is having to design, whether it be the mobile phone or the high-end supercomputer, these days the thing he has to think about probably before anything else at all is how can I make this as energy efficient as possible, which brings me to the theme of low power computing and energy efficient computing. And we're all, each one of us is suffering from this these days. So when we go on our business trips, we pick up our bags and we think, why on earth do I have to carry around all these chargers and batteries and all this extra weight? Most of what we're carrying around is actually just the power to keep our gadgets going for the length of the business trip. And if only we could improve that situation, things will be much better for every one of us who ever travels anywhere. And indeed, this has been identified by some of the top-level people studying the future of computer architecture. If you want to make very large computers, there are lots of problems to solve, but the number one issue of all is power. So energy efficiency, which will apply also in the mobile space, is really although as I'm sure you all know, my real interest is in high-performance computing, but actually there's an awful lot of synergy these days between what goes on in the mobile computing space and what happens in high-performance, simply because they're all adopting the same technology and have to deal with the same sorts of questions all the time. Now, for a long time, the problem of power and energy consumption has been rather simple to solve. So Mr. Gordon Moore from Intel, as you might even see a picture of him in Jim's spread. It's rare to find an Intel presentation without a picture of Gordon Moore in it, but we're not going to be satisfied today. Gordon Moore's law suggests that every so often the size of transistors will halve, and if we could halve the size of the transistor and also vary all the other parameters related to the transistor, like reducing the voltage, that would reduce the energy stored in the transistor. We could also increase the frequency. And in the end, when we scale all the things appropriately, we'd find out that we'd be able to increase the number of transistors on the piece of silicon, but stay within the same power envelope. And this has really driven the evolution of the power consumption of computing devices for decades. So they've always been in the 100 watts or so, or 50 to 100 watts or so level. But what's happened now is that actually that scaling has really run out now. So that there's another famous, this scaling law is actually named after an IBM inventor, an IBM researcher called Dennard. And the problem is that Dennard scaling no longer works for us. And the reason it no longer works is that the leakage current of the silicon has started to become a dominant factor. And so we can no longer perform all of these scaling operations. We can't reduce the voltage any lower, and we can't do anything much more about the frequency. So both voltage is staying fairly constant, frequency is only going up very slowly, and therefore when Moore's law delivers these smaller transistors, we don't get the enormous gains in performance at the fixed power that we were previously getting. And therefore, we need to do something more imaginative and creative. Just the old reality of cranking up the clock frequency, making the transistor smaller, doesn't deliver anymore. And therefore, what we want to like to do is to come up with some more efficient computer architectures that deliver performance in a much more power efficient fashion. And so the CPU, it has a space where it's very appropriate, and the design of the CPU architecture, the traditional microprocessor architecture, is entirely appropriate for what it's intended for doing. Going into laptops, running web servers, doing your email, all the traditional things that we do every day. And the CPU is very good for that, in particular because it's using large areas of the silicon for caches, because typically in those circumstances we're working with modest-sized data sets, and therefore good large caches, spending lots of silicon area on caches, is a good and a sensible thing to do. But there are alternative concepts of how you might design computer architectures shown on the left-hand side. And this, I've taken the GPU. I come from Nvidia, so what else would I put up there? But it's not necessarily the only way of doing these sorts of architectures, in which we are optimizing the code, optimizing the architecture for a high throughput architecture, rather than dealing with an architecture which is manipulating modest-sized data sets within large caches. And if you take this approach to designing the processor architecture, you can come up with some much more effective and efficient ways of making use of the energy consumption of your device. So, for example, in a GPU, we're using a SIMD architecture, so that you generate one instruction and then use it many times. So you're being rather efficient about the way in which you use and decode your instructions. There are very few caches on a GPU. There are small caches there, so not much energy is used in manipulating data that's in caches. The instruction flow of the device is rather simple, so it doesn't do any speculative execution, doesn't do any out-of-order execution, so the control flow within the processor itself is rather simplified. And when you start doing these sorts of things, one thing that comes out is that you have large areas of the chip here and here that are explicitly dedicated to the things you want to do, to doing the actual arithmetic, rather than having large areas dedicated to caches. And you can have, as I tried to indicate, a rather effective and efficient computer architecture. If you want to know more about this slide, I'm just going to put it up now, because but if you want to know more about it, I'll be talking much more about this slide in the next in the Nvidia second presentation, which I think is this afternoon. But we have, of course, a roadmap to take this GPU architecture up to the very high-end and very high-performance devices. But what's of much more importance in this presentation, which is about energy-efficient and low-power computing, is what we will be doing with the Tegra devices. So this is a range of devices that are intended to go into mobile phones and tablets, and it's quite likely if you bought the right phone or tablet, not Apple unfortunately, but many other devices, you'll find these Tegra processors within them. There are important economic ramifications of this whole mobile computing space. So I regret that HPC is not an area where you can really make a big income. But if you can take advantage of a large-scale consumer market, like mobile computing or gaming devices, then you can exploit that technology in lots of other interesting and a little more peripheral ways, such as high-performance computing or professional graphics. And therefore, many of the ideas that will get developed for these mobile devices that are intended to go into your phones and tablets will eventually come forward into high-performance computing devices. And in particular, a couple of things I'd like to point out on this chart is in 2014, so next year, we'll start seeing mobile devices, mobile processors containing a fully fledged Kepler architecture GPU. And then a year or so after that, this cadence of mobile processors is rather rapid, and so we have to keep up with a regular cadence of new devices, rather more frequent than some in the HPC space. We'll start seeing this thing here, the so-called Denver CPU. So this is a project that Nvidia has talked about a couple of years ago. It takes a while to produce a new processor, so it's not until 2015 that we start to see the results of it. But this Denver CPU project is Nvidia's effort to make a 64-bit ARM architecture. The reality is that by this time we're starting to see something like 4 gigabytes or maybe more memory in your mobile phone, strange as it may seem, and therefore we need to go to a full 64-bit architecture to drive your mobile phone. So these are some of the technology highlights that you might expect to be seeing coming out from Nvidia mobile devices in the next few years. Because we will have here and here an integration of ARM cores, all of these Tegra devices are based on ARM architectures, and Nvidia has a license, the highest level of license for designing and manufacturing ARM devices. Because we have this integration here coming up in a couple of years' time of GPUs and the ARM cores in single devices, what we'd like to do is already give people the opportunity to start playing with this sort of technology and see what they can make of it. So one of the things that some university researchers have been looking at, and this is an example from Barcelona Supercomputing Center in Spain, in Catalonia, is the idea of using ARM processors and mobile devices, so low-power devices, low-energy devices, to see whether they can be sensibly put together in large clusters to make high-performance devices. And so a student had the task of taking many of these boards and manually plugging together and screwing them onto base plates and then plugging in all the cables. And eventually we ended up with a complete rack of ARM processors plus GPUs. Took rather longer than the university was expecting, but they had a lot of slave labor in the terms of students, so eventually it got done. And this is the sort of building block that they used for this processor. It's a board about this sort of size. And you can see here we have an Nvidia Tegra chip here. So this is a device that has the ARM processors, a PCI connection, and here is a GPU of the sort you'd find might go into one of these laptops. I don't know whether this one is, but certainly the one that my company issues to me has one of these mobile Nvidia GPUs in it. And then it has all the peripheral things you'd expect to find, so USB connections and Ethernet ports and so on. And so you have a complete computer on a small board that can be used as a test bed for starting to look at these concepts of what can we sensibly do with this, what's eventually going to be the mobile technology integrating into a single chip, but what can we start sensibly doing with this architecture of an ARM processor coupled together with an Nvidia GPU. Some vendors have started to think, well, actually, this is a sensible thing to make a real product out of. So this is just a kit you can buy and comes in a cardboard box, and it's up to you to make the best of it. This is an Italian company. I think it actually comes from a company called E4 in Italy. Has said, well, that's what happens if we start to make a more user-friendly and commercialized product out of it. And so they've taken this board, engineered it a bit better into a blade chassis, and then you can plug all of these blades into a rack and start building up computers rather more simply than having to ask a couple of students to work for weeks and weeks putting all the wires together and screwing things together. That was the first generation of this concept. Here's the second generation device, which is called Kayla. Again, you can see the same sorts of things here. So in the center here, we have the Tegra processor, which has, you can't see it in this picture because there's a heatsink on top of it. But now we have a full-sized PCI connector here, and so you can plug into this board any reasonable GPU that you'd want to. Best to stay reasonably balanced, so it's a fairly low power processor, CPU processor, so stick with a fairly low power GPU as well. But you can go completely over the top with this, and you can install in it here how much will this be? So a 500 watt power supply. This takes, I don't know, 30 watts or something, and stick an enormous GPU on the side of it, which is far bigger and heavier than anything else. It does work, but it doesn't make a whole lot of sense to do that because the whole system becomes completely unbalanced. The whole point is really to look at what can you do with a low power, low performance processor, a low power, not so low, lower performance GPU, and then put together lots and lots of them to see whether you can make a sensible computing device out of the whole lot. And eventually you might think about the concept of then building a device out of these processors that are intended for the mobile space. So that concludes my presentation and gives some sort of ideas of where Nvidia is thinking for how we can use mobile processors in some innovative and interesting ways. And there should be a couple of minutes left over since my
there is a question.
5, so there's time for questions.
Some time for questions. If any questions. Karthik.
Yeah. One of your slides you mentioned power energy taken per instruction.
Yes.
Could you explain how you came across, how did you come to those numbers? Or is there a secret?
It's not a secret. I think it's a reasonable thing to write a program that is going to drive your processor hard and stick a meter onto it and measure it. So it's not a complicated. There's no complexity or no mystery here. It's a fairly straightforward measurement or computation.
It depends where you're measuring. You're measuring at the power supply, you're measuring at the wall plug, you're measuring at the graphics chip itself. And which is the point you're measuring? That makes a big difference. You're including the memory system power.
Yes, true. And indeed, high-performance memory systems consume a significant quantity of the energy consumption of the device.
You mentioned just now the GTX Titan card in the context of this talk about HPC. So are you a bit concerned about the Titan cannibalizing some of the sales for the rather more expensive HPC cards? There's only a couple of features that are disabled on it.
Not concerned. In fact, it was a deliberate decision, which went all the way up to the CEO of the company. So it's obviously the right decision. I'm certainly going to make no complaints about that. The point is that the Titan card is an excellent development environment of modest cost for people who, as a development platform for getting going. If you were to try to build a large system made out of Titan cards, some of the, we're quite selective and carefully chose the features which don't work, and you will find that they're very important if you want to put together a large cluster or a large system. And once you start putting many devices into a system, you start moving to a completely different regime in terms of the required reliability of the device to keep it going reasonably, to keep it going in a sensible fashion. So the Titan, excellent. We promote it as an excellent platform for one-off development, but not a platform for building large clusters with.
Okay. Thank you very much, Tim.
Okay.